Welcome to this video that provides an introduction to the characteristics of human environmental exposure data. A special type of skewed right distribution, and many exposure parameters actually follow roughly or approximately a log-normal distribution. This text in the box in orange describes is like a simple definition of a log-normal distribution. It is one in which the logarithms of the parameter values are normally distributed. So a log-normal distribution is one in which the logs of the values follow a normal distribution. A log-normal distribution can be, here's some acronyms, I guess, to abbreviations to go with it. So log-normal distribution ln, an ln, or just random variables distributed log-normal with a certain geometric mean and a certain geometric standard deviation. It's GM and GSD respectively. The geometric mean is simply the mean of the natural logs exponentiated. That's what this e raised to the mu ln x is, where ln x means natural log of a value. The mu means the mean of all the natural logs, and e raised to the mu of natural log x is simply that, exponentiate the mean of the logs. So how do you do it? Take the natural log of each observation, calculate the arithmetic or regular average or mean of those natural logs, exponentiate that arithmetic mean, and now you have the geometric mean. In a log-normal distribution, the geometric mean is equal to the median of the raw data. So if your data are indeed approximately log-normally distributed, you will see that the geometric mean, as calculated here, is approximately equal to the median of the raw data. The GSD, or geometric standard deviation, is calculated in a similar manner. Again, you start by taking the natural log of each observation. You calculate the standard deviation of those logs, and then exponentiate that standard deviation of the logs. And the GSD is generally in the range of 1.5 to 4 for exposure data, but it can be higher too, 5 or 6 or so. Not much lower than 1.5 though, because when it gets lower than 1.5, the distribution's not skewed right very much at all, and it might actually look more like a normal distribution. There's another way to estimate the geometric mean and geometric standard deviation, and that's to do so from the normal probability plot. So here's the data from the new homes. The natural log of the formaldehyde measurements plotted against the standard normal deviate. You can see they're almost a perfectly straight line, where the natural log, so the y-axis of the formaldehyde concentrations, is equal to 2.99 plus 1.09 times the z-score. So the intercept is 2.9, no, the average value, average y bar is 2.99, about right here. The standard deviation is 1.09. So that means when you step one standard deviation, like from 0 to 1 on the x-axis, the slope, the y value will be up 1.1 log units larger than the mean. So if we go over to 1 standard deviation up to the line, that's about 4, and yes, that's approximately 1 log unit higher than the y bar. So here, the mean of the natural log of x is about 3. The standard deviation of the natural log of x is a little bit more than 1. We exponentiate the 2, and we get a geometric mean of approximately 20 microgram per cubic meter and a GSD of about 3. So 2-week average formaldehyde concentrations in indoor air of this sample of new homes are approximately log-normally distributed with a geometric mean of 20 and a geometric standard deviation of about 3. You can also estimate the percentiles of a log-normal distribution using the mean of the logs and the standard deviation of the logs, as shown here in blue. It can also be done, the percentile can also be estimated directly from the geometric mean and the geometric standard deviation. Looking at the box in blue, which is calculating the percentile value from the natural logs, it's the same, the technique is the same as you would apply for raw data, except at the end you have to exponentiate your result. So we could estimate the 90th percentile of the logged values as the mean of the logs plus the standard deviation of the logs multiplied by the z-score for the 90th percentile, which is 1.28. We plug in the values for the mean and the natural log of x from the prior slide, and we get the log of the 90th percentile is 4.39. If we exponentiate the natural log of the 90th percentile, we'll get the 90th percentile, that's shown here, so e to the 4.39 is 80 microgram per cubic meter. We can also, as I said, we can also estimate this from the geometric mean and GSD directly. P90 would be equal to the geometric mean multiplied by the GSD, which had been raised to the z to the power of the z-score that goes with the percentile we're interested in. Shown here is the 90th percentile, and the z-score is 1.28. So P90 would be 20 roughly, multiplied by 3, which itself is raised to the 1.28 power. That you end up there with 19.9 times roughly 4, and a 90th percentile of 80 microgram per cubic meter. Identical or very close to the result within rounding that we got in the blue box using the natural logs. The relationship between the equation in the natural log and the equation in the blue box and the equation in the orange box is shown over here in gray. It's just based on the rules of logarithms.